11.3, we're going to be using the chi-square test to do tests of independence. A test of independence is used to determine if two events are independent of one another. And let's take a moment to remember the definition of independence. Remember, two events are independent if the occurrence of one event does not affect the chance that the other event occurs. So, for example, if you roll a dice, those dice rolls are independent. If you flip a coin, those coin flips are independent. If you draw a card from a deck and put it back in, then the draws are independent. But if you draw a card from a deck and keep it out, then those draws are dependent because that one card being missing changes the probabilities of other cards being drawn inside the deck. So the test of independence is going to be very similar to the goodness of fit test, and this is our test statistic. It's almost exactly the same, except for that we're going to sum over all possible values in the table. That's what this I times j looks like. The null hypothesis will say that the variables are independent, and the alternative hypothesis will say that they are dependent. Let's do an example. Let's find out if there is a relationship between the type of movie a person watches and whether or not they eat snacks. So we surveyed 600 people and got the following data. The first column tells what type of movie they picked, action, comedy, family, or horror, and the second two columns break it into whether they bought snacks or did not buy snacks. So for those people that watched action movies, 50 bought snacks and 75 did not, etc. So again, our null hypothesis is that snack buying is independent of movie type, and our alternative hypothesis, that should be an A, is that snack buying is dependent on movie type. All right, so we're going to assume they're independent, and the alternative hypothesis is going to be that they are dependent. The first thing we need to do is figure out what we expect to happen, just like with the goodness of fit test. To do this, we need to do some computation. Based on these results, can we figure out what would be expected for each of the category totals? Each of the category? The first thing we need to do is add up all the totals. So we totaled all the rows and we totaled all the columns. The column total should be 600 since that was the number of people we surveyed, and the row total should be 600 as well. Column totals, row totals. I'm doing my arrow backwards. The probability of choosing an action movie is 125 out of 600. The probability of buying snacks is 310 out of 600. So if we assume that these are independent, that means that the probability of choosing an action movie and buying snacks is equal to the probability of each independent multiplied together. Probability of A and B equals the probability of A times the probability of B. So let me write that down here. Probability of choosing an action movie and buying snacks, if they're independent, is just going to be the probability of seeing an action movie times the probability of buying snacks. That's going to be 125 and 600 for the probability of seeing an action movie, and 310 and 600 for the probability of buying snacks. We multiply those together and we get about 0.1076, which is about 10.76%. So if 10.76% of the 600 people both see an action movie and buy snacks, we can figure the expected value for that cell is going to be about 0.1076 times 600. So that's 65 people. And that's what's going to be the expected value for this cell. The expected value for picking a movie and buying snacks is going to be about 65 people. The book gives a nice formula for this, for what we just computed. And I'm going to go through what their formula says versus what I computed. Their formula says the expected value, so that's what this E stands for, is the row total times the column total divided by the total number surveyed. So the formula way, so that would be the row total, which was 125. The column total is 310. 125 times 310 divided by 600. That's the formula way of finding it. The way I did it, which is going to work out the same in the end, is the probability of that particular row, which is 125 over 600, times the probability of that column, which is 310 over 600, times the total number of values surveyed. You'll see that this actually turns out the same because when you do the multiplication, the 600 in the numerator cancels one of the 600 in the denominator, and you still end up with 125 times 310 over 600. I prefer to do my computation because I'm just bad at memorizing formulas, but if you prefer to use a formula, that's fine. So what we did is did this computation for all the values in the table, and I put them in bold. So this computation right here, 64.58, is 125 times 310 divided by 600. Right? So let's double check the next value. All right, let's see where this one came from. I'm going to draw a box around it. 60.42. Well, it's going to be 125 times 290 divided by 600. Grab your calculators, check that out. 125 times 290, divide that by 600, and you get 60.42. So all these boldface values are going to be computed in that way. So the 155 comes from 300, and this column is 310 divided by 690. 300 times 310 divided by 600, sorry. All right, so that's how you compute the expected values for each value in the table, and you need to do that for all 8 of those. All right, now that we have all our expected values filled in, we're going to go ahead and calculate our chi-square statistic for each of these 8 values. So the chi-square statistic, the part we're going to calculate is inside the sum, and then we will sum them all up at the end. So we need to calculate, much like with the goodness of fit, the observed minus the expected squared over the expected. Remember, the observed are at the top and the expected are in bold. So let's go ahead and calculate for the very first cell here. Observed minus expected is 50 minus 64.58, which I'm pretty sure is, I don't mean to underline that, equals negative 14.58. The next step is to square that. Negative 14.58 squared equals, I need my calculator, negative 14.58 squared, oops, I hit the wrong button, is 212.5764. All right, divide that by the expected number, so 212.5764 divided by 64.58 equals 3.29. So that is my chi-square statistic value for this cell, right? Why don't you pause the video right now and do this for the next one. Compute the chi-square statistic for this cell. All right, were you able to compute it? Did you get 3.52? I went ahead and did these for all the values in the table. So the red bold values, oh, this should be red. The red bold values are all the chi-square statistic values. And now what we're going to do is add them all up, right? Because it says to add them all up. Add them all up and we get 65.03. The degrees of freedom for this chi-square statistic is going to be the number of rows minus 1 times the number of columns minus 1. So there's 4 rows and 2 columns. 4 minus 1 is 3. 2 minus 1 is 1. That gives me a total degrees of freedom of 3. Using my chi-square statistics calculator, I plug in 3 degrees of freedom with a chi-square value of 65.03, and I actually get a p-value of 0. That's pretty low, so I guess the null hypothesis must go. So my conclusion is, at a 1% significance level, the data supports that movie type selection and buying snacks are not independent. Is there an easier way? Yeah, there's an easier way. We can use Arcibeti for this. Again, it's pretty limited. I think remember you can only put in 10 rows and 5 columns. So I did want to make sure you knew how to do this computation by hand. It's a little tedious, but it isn't particularly challenging to do by hand. And I wanted you to understand that. So let's use Arcibeti and see if we get the same thing. And it went through and it computed all the expected values, same thing that we got. Calculated your chi-squared statistic, the same as we got. Basically the same p-value. It computed zeros all the way out there. And 3 degrees of freedom. So again, we reject the null hypothesis. And our conclusion is that at a 1% significance level, the data supports that movie type selection and buying snacks are not independent. So let's talk a little bit before we finish this up about conclusions and not conclusions. The only conclusion we have is that at a 1% significance level, the data supports that the movie type selection and buying snacks are not independent. What we cannot conclude is that watching a particular type of movie causes you to buy snacks, or vice versa. Buying snacks will cause you to choose a particular type of movie. We cannot conclude in any way that one variable causes the other, only that they are not independent. All right, that's it for this section.